had, this is rho xy, this is b, and this is the integer quantum Hall effect. And the Landau level is like this is the energy versus the density of states. And we showed that if new Landau levels are built, then you see the correct quantization of the Hall resistance. And then I was convincing you that this doesn't really explain anything else. Because if n Landau levels fill these, then you get precisely the right Hall resistivity for there in the middle of the plateau. But as soon as you vary the magnetic field, you'll no longer have two or new Landau levels filled. So you'll no longer have this quantization. So the puzzle was, why are you seeing plateaus? And I mentioned in the last lecture that the answer is disorder. Okay, so what I'm going to do in this lecture to begin with is just explain how disorder gives rise to these type of plateaus. It's going to be a little bit heuristic. I'm not going to give many details, mostly because I don't know the details. Having read through them, they look very messy and very horrible, as usual, for disorder. And it's not really what I care about. What we're going to care about ultimately is the physics of what happens when you're on the plateaus rather than why the plateaus form themselves. So I'll give some sort of slightly hand-waving explanation for why we see plateaus.
And about rho xx, we concluded at the end of the last lecture that is 0 altogether.
Good. So rho xx is 0 in a... That's right. Actually, anywhere in this, anywhere else using. Okay, so what's disorder? What it means is we'll add to our Hamiltonian just a random potential. Okay, so it's just some crappy looking potential that goes up and it goes down, just in that. Okay, just some random thing you can draw. We're going to assume that the disorder is there, but it's small, where small means that disorder is much less than the separation between these lambda. Okay, so what do we expect? So we won't do any calculations, we'll just use the intuition that we know from undergraduate quantum mechanics. We have a situation with a degeneracy, and we add a perturbation to that system. So in general, from undergraduate quantum mechanics, you expect that as soon as you add a perturbation, the degeneracy is lifted. These states no longer all have the same energy, but instead they get split. So we expect in general that the Landau levels look like this due to disorder will be split. But this condition here is really telling us that the states in this Landau level are not going to mix much with the states in this Landau level. Okay, so the splitting happens within this Landau level and then within this Landau level, but there's no mixing between Landau levels induced by this disorder. So the natural thing we expect is that the density of states starts to look more like this. Okay? Where the center of these is supposed to be level with the center of these. But we can say more, because not all of these states are going to have the same properties. So in particular, let's look at some disordered potential. So this is going to be a top-down view of the sun. Okay, so this is the two-dimensional plane in which physics is happening. And there's some potential which sits on this, which is some random crappy thing. And the height of the potential, you would think of as coming out. Okay. So the potential is going to have some peaks, like this, and some troughs, like this. Or we can start to draw equipotentials around this. There'll be potentials, that's kind of a hill coming up. This is a dip. This is some sort of, I'm not sure what the right description is, but it's an equipotential. Now let's think semi-classically about what happens. So we reminded ourselves at the end of the last lecture, I think lots of you were left, about a very beautiful calculation we did in the first year of undergraduate physics. And the calculation is the following. Imagine a particle moving in a magnetic field. The magnetic field is going to be that way, so the particle does this. But imagine it, say, in gravity, so that there's the force pulling it down. Okay, so what happens? The particle goes around in circles, like this, and you might think it gets pulled down by gravity. But that's not what happens if you solve Newton's equations of motion. If you solve Newton's equations of motion, the particle goes around like this, and it drifts sideways, rather than drifting. So what's going on is in a magnetic field, if you have an extra force on the particle, and the force is small enough, the particle doesn't go in the direction of the force, it actually goes along equipotentials of the force. So horizontal is the equipotential of the gravitational force. The same is true here. We just think classically. The particles will go in orbits like this, but the orbits are going to drift along equipotentials. So the orbits will drift this way. Actually, let me get the it's important to get the sign right. Actually, they drift the other way. This is where the magnetic field coming up. So they go around in circles, but classically they drift along the equipotentials.
This doesn't depend on how strong the magnetic field is.
The strength of the magnetic field, yeah, everything here is assuming some kind of adiabatic approximation in classical mechanics, which means the variation of the potential is small compared to the magnetic field, which is essentially this condition. I think I need two conditions. I need this and the derivative. I'm just going to so there's some sort of small perturbation on that. Okay, so
The landscape will be much larger than which
this should be the same.
Same. Yeah, this is only one scale.
Okay, so that's sorry. This question. Yes.
Are the plus and minus charges or heights of the hills?
Sorry. Say that again.
The plus and minus
Heights.
Oh, they're the heights of the hill. So this is a hill and this is a valley.
Then why do the trajectories care about whether it's in a hill or a valley?
They move along.
You change direction.
Let's see. And you can see even just smoothly that has to be.
No, sure.
Yes,
Why do they change direction?
It's probably because B. I mean, in the sense that if it is sloping down, then it's going away from the peak. And then if you do V plus B, I think that arrow probably has.
Think about where the force is. So think about gravity. If gravity goes that way, which it does, the particle drifts that way. But if gravity was going upwards, the particle would drift the other way. And so the forces are either towards the hill or away from the hill, depending on where it's at.
Gradient B is the knowledge of
Okay, so that's a classical picture. Of course, you might expect that something like this happens quantum mechanically, and it does. You can certainly do very easy semi-classical quantization and look at what happens to the wave packets, and you see that it's exactly the same. So what does that mean? It means the following. It means that there's two different classes, qualitatively different classes, of states in this system. Because some states, say the ones here, the wave functions that you'll look at will be localized around this equipotential. So the states will just spread around here. Whereas some of them, like the ones on this equipotential, the states will be not localized but extended from this side of the sample to this side of the sample, just because the equipotential spreads over. Okay, so there's two classes of states. There's localized states, which just live in some small region, and there's extended states, which spread over the entire sample. When you look at it. So this is a very common theme. The theme is that adding disorder to a system gives rise to localization, gives rise to states which are just localized in some small region. This was first discovered by Anderson. It's called weak localization. This is a much simpler version of Anderson localization. It's really just happens classic. It's just due to the properties of magnetic fields and motion. Okay, so what have we learned? So we expect that the center of mass of the particle drifts along equipotentials of x, which means that we expect the extreme states. By extreme states, I mean those with very high energy or those with very low energy to be localized. And only the states near the center of the band or at the edge of the sample. So there's always states at the edge of the sample. Which will be extended. Will be extended. Okay, so what does it mean in this picture? We've drawn this picture here, and we haven't made any distinction, but out of all the states that we've listed here, most of these we expect to be localized states. And in the middle, this band, there's going to be the states that correspond to the orbit's length. These are the extended states. Okay, any questions about this? So disorder does two things. It spreads out the degeneracy of the Landau, but then it splits states into two qualitatively different classes, those that don't go anywhere because they're localized in some regional space, and those that can spread over the entire space.
The thickness of the pink band,
Yeah.
does it scale in some simple way with the size of the thing as 1 by n or something?
I don't know. My vague recollection is that the bands are much thinner than you would naively expect. There's actually very few extended states. But I'm not sure how it's. Do you know?
Roughly speaking, you should number of populating lines across. I mean, this semi-classical picture.
Yeah.
And something scaling up that would essentially.
I know nothing about it.
Yeah, I know off the top of my head, I don't recall about it.
There's a subject called percolation theory, which is exactly asking questions like this. When you get lines that go from one side to the other. I know almost nothing about this.
How deep is it?
Okay, so what does this mean? It's important for conductivity, because if you're doing questions of conductivity or resistivity, the only states that contribute are those that are going to make it from one end of the sample to the other. If you have states that are just stuck at some region of the sample, they're clearly not going to contribute to conductivity, because you put a wire here and a wire here. You get those rusty crocodile clips from school that you clip them on, and these ones are just going round and round and aren't going to contribute to transport about things that are moving. So now let's look at, as B increases, so what was the problem before? As B increased, you had more and more states available here, and what was sort of two filled Landau levels becomes one filled Landau level plus a partially filled Landau level. What happens now? The same thing happens, that as B increases, you have more and more states available here. But now what's going on is the states are tumbling down, and they can either fill the extended states, or they can fill the localized states. And if they're filling the localized states, they're not contributing to the conductivity. Okay, so as B increases, it's actually best to think about it as the Fermi energy. So the Fermi energy decreases. So what does that mean? The Fermi energy. Suppose you had both these Landau levels filled. You increase B. There's more states available here, and this is only partially filled. So the sort of the filling fraction moves from here, which was a fully filled Landau level, down to say here. So that everything below this line is filled now. But as the Fermi energy decreases, you're not changing the number of populated extended states. You're only changing the number of localized states. So the resistivity or the conductivity isn't changing until you finally hit the extended states. So as B increases, the Fermi energy decreases. Only localized states change their population number. Which means the conductivity is expected to remain constant. Okay, is this clear? This is the reason you get these plateaus, the Fermi energy changes. It's only the localized states being affected. Except, we still haven't explained the fraction of the integer quantum Hall effect. So what have we learned? We've explained why there are plateaus. This explains why, as you change the magnetic field, the conductivity doesn't change. It's because the number, the extended states don't change their population. But it doesn't explain now what we'd originally started off, which is why the whole conductivity was quantized to begin with. So it explains the plateaus, but now we've lost the reason for quantization.
So you're saying that you would naively have thought that the conductivity decreases?
Of course it should decrease.
Because fewer things are moving.
Fewer states. Yes, I think you got it right. I'm not sure. Yeah, fewer states which are contributing. But now we've lost the explanation of quantization. And why is that? It's because when we computed the conductivity, we assumed that every single state in the Landau level contributed to the conductivity. And now the states aren't contributing to the conductivity. They're localized. So the naive guess is that as soon as you have disorder, yes, you get plateaus, but the position of the plateau is no longer in this quantized value. It should just be any random thing coming from this random system.
David, I'm really sorry I was late, but I'll just quickly ask you one or two things to catch up. So you said that the Landau level band splits and half of the, some of the states are localized while the others are extended?
Yes.
Now, I want to understand that. In what sense were the original Landau level states extended? What is the difference between them?
Let's look in Landau gauge at least, where it's very clear. In Landau gauge, all the states were extended in the y direction.
So it is possible to make states that were extended, but now there are some states which, right. Now you break the degeneracy, so the states are just states.
Yes.
There's no ambiguity, and some of the states have localized.
Just because they drift along equipotentials, and so they're very basic reasons. They're localized. And there's very few which extend across the whole sample, and it's only those few which can contribute to it.
I suppose the thing that confuses me is that classically, all orbits were anyway localized. Okay, but you say because the degeneracy of the classical intuition is very bad.
Yeah, I think that's true.
Okay.
Well, one could think there are some.
states out of those degeneracy.
Yeah, I know.
You know, even classically, there's some orbits which are not localized, which are those at the edge. So you have the edge of the sample like this, and
I think as the velocity increases, the radius increases, and the largest. The edge.
so
Edge.
it hits.
Oh, I see.
And you know, it's not going to leave the sample. So what can you do? It can't bounce back this way. It has to bounce this way.
Right.
So the edge modes are never localized, and actually here as well, the edge modes are playing.
Fine. But the bulk modes were all localized classically. Yeah,
But because of the degeneracy, it's not such.
And you explained that you put any random disorder, this localization will happen. That's a theorem. That's obvious.
I don't know. It smells obvious by drawing pictures.
Kinetic energy is zero. I mean, it's competing with kinetic energy. In some sense, in random levels, kinetic energy is zero. Flat band.
I see. So things just settle down to where they can. I see. Thank you.
Yeah, so the magnetic field here, even in the previous picture, has two effects, right? One is that the degeneracy of every level is increasing, and the other is every level is also shifting down now.
Shifting down.
Because the gap is
increasing.
h cross omega.
Say that last bit.
The gap is h cross omega, right?
Oh, that's true. Do you know, it's sort of conceptually a little easier, I think, to think about fixing the magnetic field and changing the chemical potential by changing the density of states. Because you're right, too many things are changing when you change the magnetic field. This shifts as well. But we're always assuming that this is shifting, but these are not mixing with these. This is much bigger. It doesn't look like here, but this gap is much bigger than this. Right? That was the formula I had. V is much smaller than H.
So the extended states come into picture when you are at the end of the plateau. You are going from one plateau to another, right? Roughly speaking. One picture is that it's all edge modes that gives you the quantization, which and there's this picture also.
I'm not sure I believe that calculation about the edge modes. We can talk after it, but I think that if you look at it, it's sort of the calculation. There's a calculation you can do which is all the conductivity comes from edge modes. But I think if you look at it, it assumes that nothing comes from the mold. And you can certainly add things where you get contributions from the modes.
I mean, if the analogy to percolation is good, then there will be a point in which there are no percolating lines at all. So, and then it's only the edge fellows which will be extended. So, what is that criticality here? I mean, what do you do to random potential? Too many peaks and troughs, or what? I mean,
it's that criticality is supposed to be when you hit the middle extended state. That's equivalent than hitting the middle extended state.
Well,
extended state is coming from
now there will be no extended states at all, right? I mean, if there are no percolating paths at all.
The percolation picture, I think, comes from a slightly different perspective. You have these troughs and valleys, and now you think about throwing in particles, fixing the magnetic field, and changing the Fermi energy. So then you think about this kind of sea lifting up. Firstly, it sits in the troughs, and eventually it will lift, and everything will join. Will join together. And I think in that picture, when you get those extended states, that's here, and that's when you jump from one plateau.
So the extended states in any band are higher energy than the localized states?
The argument here was suggesting that the high energy ones and the very low energy ones are the ones that are localized.
The ones in the middle are the...
Okay, so what's going on? It sounds like we've managed to come up with a fairly convincing argument that integer quantum vortex shouldn't exist. The plateaus should exist, but there's no reason for quantization because you have fewer states contributing to that. So something miraculous happens. The miraculous thing is that although there are fewer states contributing, each of those states steps up and conducts more in exactly the right way to give back the quantization. So it really sounds amazing. This happening. To my knowledge, there's one very precise calculation you can do where you can see this, and I'm not going to do it on the board. But the precise calculation is where you don't put a random potential, you just put a delta function potential. And then you can compute very explicitly that there are localized states around the delta function potential. Most states in that case are not localized, but those that are not localized precisely pick up the amount that they conduct to give back the missing.
I think there is another calculation just from diagram analysis where you just put random impurities with delta function potential at random location.
Nice.
And then you can do basically a diagrammatic calculation and show that if you just calculated the bare bubble, in that sense you would have gotten something else. But if you do the disorder vertices carefully, the vertex correction which exactly cancels and gives you back the compensation.
So that sounds much more.
Yeah, that's the one.
There's some kind of one loop effect. That
Yes.
gives you
So this one simple way to understand this, apart from doing
Yeah, we'll
like,
do
there's no conservation.
we'll do the simple way now, of course. I'm not going to do the complicated way. I'll do the simple way. Yeah. Okay. So let's see why this is happening. And the simple way is an argument due to Laughlin. We'll see. Laughlin was a big figure in the 1980s, literal, figurative sense. He did some important work on the integer quantum Hall effect, which we'll next see, and then he really sort of did the pioneering work on the fractional quantum Hall effect. Okay, so let me tell you Laughlin's argument. And so we're going to do Laughlin's argument, which is nice and simple, and then we're going to do some much more mathematically sophisticated and beautiful arguments to see why, in general, this should be. So it's called Laughlin's gauge invariant argument.
Can I ask you?
Yeah.
So these extended states, you're saying they contribute to the rho xy conductivity.
Yes.
But don't they also contribute to the xx conductivity at the same time? But then the graph shows that it's either xy or xx.
I think rho xx is always zero when you're in this insulating state. Let me see. We decided in the last lecture that when we computed rho xx in just an empty Landau level, we got zero. So the question is now, why would you expect that to change if? So suppose your Fermi energy is here. So Fermi energy is buried. So that's when you're on a plateau, when the Fermi energy is buried in the localized states. So these extended states, I think the same argument holds.
So the extended states are when the part between the plateaus.
Part between the plateaus is when you're lying, when the Fermi energy lies within this. So the number of extended states are changing. That's what you do. Okay, so the argument. You'll see, all of these arguments for the quantization of the integer quantum Hall effect all require us to go to a slightly special geometry. And it never quite smells right, because if you have the right argument, it should hold for any geometry. And yet you need slightly different arguments for different geometries. And so this is the first example we'll see in this. So the argument is the following. We'll consider the annulus. The annulus is a disk. Very badly drawn disk. And it's this disk which is going to be the quantum Hall state. So in this disk there's going to be a magnetic field, V, which passes through the disk. And let me introduce some coordinates. This is R and this is phi. And we're going to argue that the Hall conductivity of this disk is necessarily positive. And the important point about having a disk is that there's kind of an extra handle you can add to the system that allows you to explore a little bit. And the extra handle is something that we looked at in the last lecture. It's putting a flux tube through the center of the disk. Okay, so this is a solenoid, and it has flux phi through the center. So this is exactly the kind of thing we were looking at in the last lecture when we were looking at particles moving around flux tubes and this idea of spectrum. The same idea is going to be important. So this is the game. We start with this. Well, we're going to start with the flux phi being 0. Okay? Things here are going to sit in an integer quantum. We're going to show that they sit in an integer quantum Hall state. So we start with the flux phi being 0. So we slowly, this is the same kind of adiabatic game we played in the last lecture, increase phi from 0 to that quantum of flux phi 0. Now the thing that's special about the quantum of flux, remember, is that the spectrum of any Hamiltonian of particles outside remains exactly the same when phi is 0 and when phi is phi 0. Spectrum is unchanged. So the particles here can't tell the existence of one unit of quantum flux. So phi 0 is 2 pi h bar. Okay, and we slowly means a time which is, again, much bigger than splitting 1 over h bar. Okay, so some very basic undergraduate electromagnetism says that changing a flux from 0 to something induces an EMF in the system. EMF is one of those things you learn about when you're an undergraduate and then forget about. At least if you're a string theorist, you forget about it approximately 2 months later. And then so it induces an EMF. The EMF is minus phi by dt, which is, in this case, we'll just increase linearly, so it's minus phi 0 divided by t. This is the time t. So now let me give you the argument. Suppose that as you increase phi from 0 to phi 0, exactly n electrons move from the inner edge to the outer edge. Suppose that was true. Surely we're going to show that is true. So if n electrons are transferred from the inner to outer ring, then the radial current is I in the radial direction, IR, minus n number of electrons transferred times the charge of the electron divided by the time it took them to get there, which means that the Hall resistivity, which is the EMF that's induced divided by current, is 2 pi h bar over e, 1 over n. So if we can argue that as you increase phi from this to this, exactly n electrons make their way from here to here, then we've got what we wanted, quantized for quantum. So our goal now is to argue that this actually happens, that precisely n electrons make their way across it.
This rho xy is to be viewed as rho r phi.
Rho r phi, exactly, yes. So this is the result that we want. So how can we show that n electrons are transferred?
N is what? N is the number of electrons in a...
N is just the number of electrons that go at the moment. Of course, we're going to have to argue that n is equal to the number of lambda electrons if we really want to make this argument. All right, so what I'm going to do is twofold. Firstly, I'm going to consider the case with no disorder and just show, using a slightly different technique, that n electrons are transferred. And then we'll add disorder, and we'll see that even though there's disorder in the system and fewer localized states, you still get n electrons being transferred. That's the strategy. So now let's consider the case with no disorder. So in the symmetric gauge, which, as we have radial symmetry, is obviously the right thing to consider. We saw in the first lecture that the wave function of z is the m e to the minus z squared or d squared, which is e to the I m phi r to the m e to the minus z r squared. Okay, so these are peaked. We saw in the last lecture, we just looked at where these wave functions are peaked. That are approximately square root of 2m v squared. So now we don't get to pick all m starting from 0. We've got to pick the m such that these wave functions actually lie within the ms. We need to choose m such that these lie in the ms. Okay, so what happens? Well, we figured out in the last lecture what happens when you increase the flux from 0 to phi 0. You get spectral flow. The spectrum is the same at the ends, but if you start in one state with phi 0, you've moved that into another state by the time phi increases to phi 0. So from our earlier discussion, of spectral flow,
so these are the states of the lowest Landau level?
these are the states at the lowest Landau level, but everything I'll talk about will go for the higher Landau level. So phi goes from 0 to phi 0. The state which is psi m, where m is the angular mode when phi is equal to 0, goes to when you increase phi, so the state that you did call phi m is the same thing as psi m plus 1. So you undergo this spectrum. Okay, so in the lowest Landau level, what we've shown is that a single electron moves from the inner ring to the outer ring because every state gets shifted up by so in the lowest Landau level, a single electron moves from the inner to the outer ring. Okay, which was precisely the result that we wanted if all conductivity was to be quantized as nu equals 1. And you can show that exactly the same argument still holds for all field Landau levels. So in general, the number of electrons that's transferred is integer, and it's equal to the number of Landau levels. Alright, so we haven't done anything new. All we've done is just rephrase the old argument in terms of a slightly different language. But now it's a language which generalizes immediately to having the presence of disorder and seeing the same thing. So I'll do the disorder calculation next. Any questions?
So suppose phi is in between one of these things. The wave function can be thought of as z to the b m plus alpha, where alpha is
If phi is between, the spectrum is not the same.
right.
Inside.
So
there's two ways to think about it. You can either have single valued wave functions, which is the way we worked last time, in which case the wave functions remain exactly the same, e to the I and phi.
but you have the magnetic field.
Their energy shifts.
The A is there.
The A is there.
But you could also gauge away the A except at a point, in which case the wave function would just become z to the power I m plus alpha, and then there would be a discontinuity at the one place where you have.
Yeah, but then you have to worry because you're not working with single value wave function. I always find that way of thinking much more.
But that's the thing that makes the spectral flow very clear. because alpha is increasing from 0 to 1. And then suddenly there's no discontinuity.
I prefer to think of the wave functions as being the same, with the spectral flow being the spectrum rather than the wave functions. Okay, so let's repeat this with this one. Yes.
In Shirada's way of looking at it, the spectrum still flows as well, right? If you take z bar n plus alpha, even in that case the energy shift, right? It's not that the energy shift.
So the energy is an invariant object. The spectrum is an invariant object. It has to be the same.
Yeah. In my way of looking at it, there's no A. So P and V are the same. Energy is V squared. In David's way of looking at it, it's not P squared. Yeah.
Okay, so
energy is always V squared, but it's not always P squared.
So the Hamiltonian is E by phi. So there's two terms in the angular. B is the magnetic field that's sitting inside the Hall sample, and capital phi, which remember has nothing to do with it, is the flux which we're threading through the center. R squared. And then there's the promised random potential that we don't care about. Well, we care about what it does to the states. Okay, so what happens? The states split into two types. There are the localized states, which sit in some region of this ring. And there are the extended states, which in this geometry are the states which go all the way around the ring. Okay, so the extended states encircle this flux, which is in the middle. The localized states don't. The localized states just sit aside.
Sorry, David, I was spacing out. So you see, the spectral flow tells us that everything moves one up. And just what was the connection between that, moving an electron? The lowest guy should be followed as the ring inside and the highest guy outside.
Exactly, because the wave functions are z to the n.
Yeah. And should I really think of this as an edge mode moving to another edge mode?
I haven't treated edges carefully in this description. I think the answer is yes. Do it more carefully about what those edges are, how they're acting. Yes, it's well, everything shifts one. I don't know if you want to say that's this edge goes to that edge, but everything moves up.
Everything moves up, but we want to say that. I see, but we want to say that means that an electron has gone. You're saying everything's moved a bit.
But physically, an electron has left the inner edge and has emerged on the outer edge.
Right.
So why only one electron?
Because we just have one field left.
You're going to n plus 1.
Yeah.
Each random level, the argument has to one shift by one.
The states are like concentric rings, and the inner state has become unoccupied and moved.
No, but his question is, how do you know that shift corresponds to 1? It's not so clear. And in the sense that, I mean, it's moving a little bit in distance.
Move more than one electron?
And each state has precisely one electron.
Each state has that's what we showed last time, that if you go from 0 to 5 naught, m goes to m plus 1. So each state has only one electron.
Yeah.
No, but it's a question of how many, like the edge encompasses how many of these states. The whole calculation is a bit approximate because we're talking about
We're careful about the edge.
edge, and the whole phenomenon is associated with the edge. So if the edge encompasses 10 states.
I'm not sure what that. You mean if the edge is of order L10 times
Yes. I mean, it's a question of what the boundary condition does. If the edge changes things over.
Suppose you just think of having filled states from some minimum m all the way up to some maximum m. Then you increase this. The minimum m will increase by 1, and the maximum m will increase by.
And the association is that the minimum m. Yeah.
There was no degeneracy?
But
there's a degeneracy, but in the energy, but not in the position. The position is telling you which state is.
So even if you were to associate the bottom 10 states with the edge, now it's bottom 9 states, so one has moved. So it doesn't.
Okay, so now we come to this key distinction again between localized states and extended states. So the flux phi does not affect the localized states at all. So why is that? I have some wave function, which was some eigenstate in the presence of this potential, but some localized wave function. And if I have phi, I can always just gauge this contribution away. Capital phi times the flux, little phi is the angular variable, and over 2 h bar sine phi. That in the presence of phi, if this, well, let me say this, if this solved the Schrödinger equation in the absence of the flux, this will solve the Schrödinger equation in the presence of the flux. Why is it important they're localized? It's because we've got phi times little phi. And I'm going to insist on having single valued eigenstates, which means that I only get to do this gauge transformation and retain the single valuedness of the eigenfunction with phi being some intermediate value. If this state does not have support on all phi, if this state had support on all phi, I'd be in trouble because when I came back it would be single valued. But as long as this state is only localized in some little region and doesn't spread everywhere, this is a perfectly welcome idea.
So in this case, the localized versus extended doesn't quite have the same thing of transporting across, because when you're thinking of extended, you're thinking
that's right. It's extended
along the ring. It's not the transporting ring.
Okay, so if psi is localized, it's only got support some finite phi. So that's important because then this wave function remains single valued.
Maybe another way of saying it is that all that the B field inside does is affect the boundary condition as you go around.
Yeah.
And if it's localized, you get it.
Exactly. Yeah, in your way of thinking.
Yeah.
When you're saying that the previous argument is not really correct,
No, I'm saying that this argument.
but they're completely opposite and they're giving the same result.
So when you are thinking of these extended states, these are not the things where you can semi-classically think that you are passing through this extended state from the inner edge to outer edge, because these are extended in the phi direction, not in the r.
This is the extended state. This
Previous
is
argument is not really the right picture.
Previous
Right
argument,
position.
It might be geometry dependent.
I think the previous argument is the right picture where you are going from one plateau to another. That's where all that activity is taking place.
Okay, this picture
This picture is.
still, but we are like completely opposing pictures with then two aspects of the same phenomenon, which is
I think that the extended thing does different things here than there. Here it encloses a flux. Here it is going from one end to another. Affecting things. They don't play the same role.
oh, the one picture has to be correct, the other wrong, right?
The picture is correct at the area of the plateau. What do you want to respect?
Oh, okay. But what is actually happening? These are just
Okay, so the extended states, we can't use this argument because this gauge transformation wouldn't be single valued, which means that these extended states are the ones which have to worry about the single values or about the boundary condition, and it's these extended states which undergo spectral flow. So not all states now, but just the extended states. So there's fewer extended states. But the net result has to be the same. Although there's many fewer extended states, each of them moves to the next one. There's at least one extended state on the inner edge, at least one extended state on the outer edge. Whatever's happening in the middle, that inner extended state must have shifted one, and the outer extended state must have been next.
How do you know there were extended states at the inner and outer edge?
There's always extended states on
Edges.
on the edges. If you think about the potential just lifting there.
When you say that fewer extended states, I thought there would just be one more extended state on the outside.
Sorry, say that again?
Wasn't your picture that the number of extended states on the outer edge increases so that the total number of extended states is the same?
No. So let's look at this annulus.
Fewer because of impurity.
So before every single state was extended, some of them at least are localized, and in fact most of them will be localized. What are the extended states? There's one or maybe several here, and one or maybe several here, and there could certainly be others in the middle, many. And the whole point is we don't care. That however many there are, this one moves to the next one, that one moves to the next one on the spectral flow, and so everything shifts up one, and it doesn't matter how many there are.
So their occupation number doesn't change if
The occupation number of the outside one exchange does change, right?
This one was occupied to become empty,
but everything else is between.
Oh, right.
I just by 0. Net result is that just one electron moves. Which is the answer we wanted. One electron for the lowest Landau level, one electron for every Landau level. So it's the demonstration of this kind of miracle happening. There are many fewer extended states, because each of them steps up, conducts more current, which in this picture is the statement that they kind of leap further with each spectral flow, so that the total conductivity is
It's just a naming change. I mean, let's say the lower rim guy is m equal to 10, and the outer rim guy is m equal to 100 or something, and in the middle there is an m equal to 50.
Yeah.
But you don't care about what it gets renamed to.
Yeah.
I mean, it's just that some 9 comes up to become 10 now, and some 99 comes up to become missing. So there is an overall net flow of just 1 once again.
So these extensions I don't care because they're always occupied in junction.
Because the middle never mattered, even in the earlier,
Didn't
without
matter, right.
integrity.
Yeah.
It's just that one fellow came out from the hole in the inner ring, and one guy.
There was no change in occupancy. It was just the electron that was doing the occupying, but you don't care which electron.
But I think there will be other extensions in principle once you break the symmetry. There will be other extensions that won't just simply go from the inner edge to the outer edge. And the radial extender state can be possible. And that's at the edge of the plateau where you're going from one.
Then you don't have the quantized gap.
Then you don't have it. Those guys are
All right, so this is kind of the first hint that there's something deep going on in this quantum Hall system. We're using sort of very beautiful arguments to do with the topology of gauge transformations, single-valuedness of gauge transformations. So it's the first time we start to see there's some powerful mathematics and powerful ideas that are underlying this.
So here's a non-trivial pi one of the geometry was important.
That's what allowed us to make this argument, was changing the geometry so that it had some topology. Okay, I'm going to move on with this this general theme of topology underlying quantum Hall effect, and we're going to discuss something called Chern classes and how we can think about the conductivity in terms of Chern classes.
So these are totally, almost completely depends on the geometry. Right?
Yes, we can't make this argument
Are
for
there similar arguments for any other geometry?
We'll see other geometries now, but if your simplest geometry is just a disk, I don't know how to make such an argument. Of course, Laughlin says in his original paper, the system is the same, so if you can make the argument for one geometry, it must be true for all geometries. But I'd rather say if the argument's correct, it should be valid for all geometries. And somehow, it's not like the argument's not correct, but it feels like it's missing. So you can't use it.
For the original rectangular geometry, you can't.
I don't know, a disk would be easier to work with, but I don't know how to.
You have to have a hole in between to penetrate your classes. So you then make this
But by the way,
they take continuous limit, the code goes to 0.
you can make that argument that this is an infinitesimal solar lines. one other comment. If you want to use this same argument to talk about the fractional quantum Hall effect, so that it's nu equals a third, the same argument tells you that 1/3 of an electron must have transferred from the in to the out. How can that possibly be? We have a third of an electron. We'll see in the next couple of lectures that that's exactly what happens. 1/3 of an electron gets. Okay. Hi, how are you guys doing?
Sorry, I didn't know the lecture started at 10, so I'm really sorry.
But I'm going to start a completely new topic now.
Okay, all right.
Which
I was summarizing it.
Sorry, thank you, Sharon.
But one that's nice, a bit cleaner, I think, than what we're about. Just one that should appeal to our theoretical sensibilities a little more. Okay, so any questions about Mulligan's?
And it's clear that this m goes to m plus 1 in the case of the impurities, that this m is still associated with position.
You probably have to work a little harder to see that, but it should.
It should. I mean, that leaves the nature of the wave function.
Yeah.
And the nature of the wave function is totally coupled up.
To do with angular momentum, and the angular momentum should be tied
with pushing things out.
So yeah. It's the angular momentum. Although angular momentum is not valid, it isn't a good quantum model with disorder. So I think you have to work a little harder. Okay, so. G. And we're going to talk about an amazing formula called the TKN anypair. Okay, so there's a much better way to see this quantization. To do this, we're going to use slightly more sophisticated techniques, both from mathematics and from condensed matter physics. I'm going to need a formula, which I have proven in the printed notes, but I'm just going to state here. And so the formula is the Kubo formula. Who's never seen a Kubo formula? Okay, so what are Kubo formulas? They're very simple. It's perturbation theory in quantum mechanics or in quantum field theory that allows you to compute the response of a system. So a very simple setup. You have some system and you want to compute the conductivity, which is what I'll write now. So what do? You take that system and you perturb it by an electric field. And then you want to compute the expectation value of the current, having perturbed by the electric field. So there's a very simple, basically one first order perturbation theory calculation you can do, which tells you what that expectation value is in terms of various correlation functions. So that's a general Kubo formula. Let me just write down the answer here that we'll need. But if you want to see the derivation, like I said, it's just first order perturbation theory, it's in the printed notes. So we'll need Kubo formula. So I should say there are Kubo formulas for anything you could want to measure, for viscosity, for conductivity. The Kubo formula we'll want is the Kubo formula for all conductivity.
So you avoid writing there.
Sorry?
You avoid writing.
Oh, yeah. Let me write it. Okay, so sigma xy is pi h bar. So how should you think about this? This isn't a formula now for a single particle system. This is a formula for a many particle system. They don't have to be free. This formula holds if they're interacting or if they're free. 0 is the ground state of your many particle system. Okay, so if you're thinking about free particles, it's really saying it's the ground. If they're fermions, each particle isn't in the ground state, but this is capturing the full complexity of that ground state wave function, which, for example, if it's a Fermi C, is one particle in the ground state, one particle next to it. It's the ground state of the full quantum system. And n is just the excited state size. And what you have to compute is, roughly speaking, the commutator of Jx and Jy. Okay, that's roughly speaking the Kubo formula to compute the conductivity for X. And then you divide by these energy squared, which is something familiar in motivation. Okay. So the proof is in the printed notes, but this is the formula we're going to need. Any questions about the interpretation of this? Okay, so the beautiful fact is that this is related to topology.
So sorry, David, this is just the standard Kubo formula involving the retarded Green's function omega going to 0. Written like this.
Almost. It's usually the one you're used to has got an e to the I omega t. So you take omega goes to 0, you expand that formula in the small omega limit. There are two terms. The first term goes as 1 over omega. And that's the term that, for the usual conductivity, tells you that there's a delta function holder in the conductivity, and the imaginary part goes as 1 over omega. That term vanishes for the whole conductivity. The next term, which is finite as omega goes to 0, is this. And the other terms go to 0.
Yeah, that's just saying this is a static phenomenon. You don't need time dependence to understand it. You don't need it. You can really take omega to 0.
But the En minus E0 whole square is coming because you have to take it carefully with it. Otherwise, you should have got usual, it's a density correlators, you would have gotten just En minus E0 in that phenomenon.
And that's the piece that
that's the bit that. So there's a slight bit of more than that.
I would have thought the leading 1 over omega piece is the dissipated contribution. At least its imaginary part is the dissipated.
That's exactly right.
So that, of course, has to vanish.
Yeah, but this is something you can compute in Euclidean theory. You never need time dependence.
But I think that's related, right? Because it's not dissipated.
So the topology we're going to relate it to is something called the Chernow buffer. I mean, you want to.
At least if it works, it's necessary.
And there's going to be two ways to do this.
Basically, you could pull this out from the partition function of your system in the presence of a constant time-independent A0 and AI field, right? No?
Because if you put A0 time independent, there's no electric conductivity, it still needs time independent A.
What about del I A0?
All I can tell you is I tried to do that and I couldn't derive this formula. I had to put in omega and then take the omega goes to 0 limit, and it's probably because I wasn't smart enough. But I did try. It seemed like it would be simpler to derive it that way, but I wasn't.
Because if you have completely time dependent vector potential, then there's no electric field.
No, but you can have A0 as a function of Xi. That gives you an electric field.
Yeah.
So if you just take the quantum field theory, put it in A0 as a function of Xi and AI as a function of Xi, purely Euclidean calculation.
Yeah, that you can.
Yet you're turning on electric and magnetic field. So you surely should be able to do it.
I think you get the density though, right? Because you've got A0 coupled to the density, and the density doesn't appear here. I couldn't make it work, but there should be a way to.
Del I of A0.
Yes, that's it.
That's
Okay, so what are the two different calculations we can do? Both of them involve a change of the geometry of space. So the first one is you can make space twice. And the second one is you make space a lattice. And in both these cases, there's a way to relate the Kubo formula for the conductivity to something beautiful in topology. Both of them are in the printed notes, but I'm actually just going to do the second one in these lectures. The reason is twofold. Firstly, this isn't going to be that important movement. It's something we'll do here, but it's not going to play that much of a role in the fraction. The reason to do it at all, however, is that this calculation, which was done in 1982, a long time ago, is really the essence of topological insulators. So this has been an enormous field in the last 5 or 10 years in condensed matter physics. And the heart of topological insulators is already in this 1982 paper by Dowders. So what I'd like to do is just tell you about that, because it's completely beautiful. So we'll choose the latter. So we'll choose.
So is it what is the point? You can either make it a lattice which is then identified, the lattice torus, or was it?
No, it's like the space is continuous in a torus.
Okay,
or you make it a lattice, and either one of those there's a calculation. In some sense, the spatial torus is a little more powerful, because the spatial torus, the calculation holds for an arbitrarily strongly interacting system, just as the Cooper, which sounds like a very strong result. In fact, it's so strong, it's very hard to see how you could possibly get the traction of quantum effect, because this seems like such a compelling argument that it has to be. I can tell you later why. There is a supplement. But for the lattice, we need to work with non-interacting electrons. We're going to work with gluons as a standard thing. Okay, we'll work with the lattice, and this captures the essence of topological insulators.
With the lattice, I'm guessing you're going to work with periodic boundary conditions. Isn't that a choice?
Yeah, but what's key is that the momentum space.
Momentum space.
That's really what the whole thing hinges on. Okay, so recall that on a lattice, the momentum lies on a torus, or lies in a torus, or is parameterized by a torus. And the torus has a name, it's just called the Brillouin zone. So this is our lattice. I'm just going to take a square lattice for simplicity. This is going to be A, this is going to be B, and just standard condensed matter undergraduate physics tells us that the momentum in this direction is periodic valued with periodicity 2 pi over A. And momentum in the y direction. And the crucial part is that it's an inequality here and an inequality here and an inequality or equals to here, because momentum equals minus pi over A is the same thing as momentum equals pi over A. Physically, because you can just impart some momentum onto the lattice, shift yourself backwards. So let me remind you about very basic things. Bloch's theorem states that wave functions can be written as a wave function is labeled by the momentum, the lattice momentum, and Bloch's theorem says that this is equal to e to the I kx times some function that itself is a periodic function of the lattice. So uk of x is equal to uk x plus e, where e is either of the lattice basis vectors. Okay, so the wave functions themselves don't have to be periodic, but they're related to periodic functions of the lattice by this simple. Okay, so then we're going to assume a bunch of things. So this obviously is for a single electron. We're going to assume that we're working with non-interacting electrons. And we're going to assume that we're in an insulating state. Okay, so what does that mean? Always with a lattice you get bands, and you fill some bands so the fermi energy lies between bands. So we have an insulator and non-interacting. So a very, very simple system. Okay, any questions about the general system? Right, so let me tell you the results of PK, N, and N. So the first thing they said is that over the Brillouin zone, for each band over the Brillouin zone, which is a torus, you can define a gauge connection. And the gauge connection is a barrier. So for each band...
I'm really sorry, I've forgotten my introduction. What are the different Brillouin zones then? In each of them, K takes this value, and the UKs are different, is it?
No, the UKs are... So the Brillouin zone labels the momentum of the particle. Let's consider a simple situation. Suppose the particle, it's what's called the tight binding approximation. The particle can hop on the lattice. Okay? So the wave functions take this form, where K lies within this Brillouin zone. In that case, there's just a single band. The spectrum which did that now does that. And in that case, our band is here. Now you can consider more complicated examples where the lattice wasn't a square or something, then you'll get several bands. Or you consider the situation where you're starting with the free particle and you just put a periodic potential, then you also get many bands. Then that turns into... You remember these pictures?
Yeah.
So that, there's lots of situations we can consider, but in each of them there's either one band or many bands, and each of those bands is labeled by a quantum number, which takes values on a torus. Does that job remember? Okay, so for each band, we find a Berry connection. Okay, so what's a Berry connection? The Berry connection before was something where we took the state and we differentiated with respect to parameters of the Hamiltonian. Okay. Here it's a little bit different conceptually. We're not going to differentiate with respect to the parameters of the Hamiltonian. We're going to take these states that we call UK and differentiate them with respect to the momentum. Thinking of the momentum as playing the role of the parameters. And so what have we got? We've got the Brillouin zone, that's a torus. At every point on the Brillouin zone there's a state. That corresponds to momentum, it's the state in the system of that momentum. And this Berry connection, roughly speaking, is capturing how the phase of that state changes as you move around the Brillouin.
Apart from this e to the ik dot x.
Apart from this, right, you've got to factor that out, so it's what's left. So the field strength.
But can I just ask you something? Okay, and then I guess the relevant gap here, if you're going to use this in some adiabatic sense, is that between the band and the next one, which is wherever.
Yeah, although we're not going to vary. Yeah, that's another difference. In the Berry connection, we thought about changing those parameters slowly. There's no sense in which we're doing that, but it is important there's a gap, nonetheless, because this is going to be a well-defined topological property only if, in some sense, the system is there's no singularities. Okay, so the field strength. So the system is just two-dimensional. That means the Brillouin zone is a two torus. The field strength only has the xy directions, where this really means kx and ky now. It's a field strength over momentum space. And it's given by what you usually have, which if you write it in terms of in terms of overlaps of wave functions is the following. So here's the claim. Actually, let me first define another thing. Given a field strength, we can define the first Chern number, which is a very fancy way of saying you just take the field strength and you integrate it over to class. I'm going to define it with a minus sign, just so things work out nicely. So there's a Berry phase over the torus. We can associate a field strength to that. We integrate that field strength over the torus. This, on general grounds, is an integer. For the same reason a Dirac quantization. Take the field strength and integrate it over the closed cell. This is U1 field strength. You always get
The physical reason is not here that you can move the state slowly and you come back? No.
No, but you can think about sort of writing this in terms of these with certain patches. And remember that Dirac argument where you have a gauge field on the north pole and a gauge field on the south pole, and you want to patch them together with a single value gauge transformation. You can play those kinds.
Okay, I see. So this is defined up to the phase of the state, etc.
Exactly.
So, David, presumably the most general notion of the Berry phase is not like there should be some parameter in the Hamiltonian, but the wave function should have some parameter. So here, wave function is the parameter for k, and you are very, it's not, the origin of that is not from something in the Hamiltonian.
I think so, although what we'll do shortly is, because k is a quantum number, we'll see we can actually write down an auxiliary Hamiltonian where k does appear as a quantum, and then it looks a little more like very, but conceptually it's a little different to this. Okay, so here's the claim. It's a claim by TKNN. TKNN stands for Dowless, Kokomoto, Nightingale, and one of these Dutch names that no one else knows how to pronounce it. It's written in Nijs, and it's probably pronounced Inbus, something like that. And the claim is completely gorgeous form. It's the following: that this very abstract object that we're computing is the Hawk. Or more precisely, if you have some number of filled bands, to each band you can assign a Chern number. So each band gets assigned an index through this Berry phase procedure, and you sum over all filled bands. So it's really astonishing that something so abstract and mathematically beautiful really has such a very direct physical consequence.
So C alpha was the Chern number with each band.
So C alpha is the Chern number for the band alpha. So here I just defined it for one band, and this is a more general formula.
And the bands themselves were in the absence of a magnetic field.
We haven't mentioned magnetic fields. That's right. In fact, what I'm going to do is I'm going to prove this, and then I'm going to give you an example where you get Hall conductivity without any magnetic field. Which has become quite a famous example in recent years. The obvious thing to do with this is you take a system on a lattice and put a background magnetic field, and you produce the kind of results that we see. That's extremely complicated. For reasons we discussed in the first lecture. The spectrum is this horrible Cantor set in general, but it depends on whether the flux through a lattice plaquette is rational or irrational. It's very complicated. So I go through it in the notes, and I give the answer for this in the notes, but I didn't have the stamina to go through the derivation. But even the answer is hard to say. It's hard to, the answer to compute this for a particle or a lattice in the background. It's hard to state the answer, and several pages to prove the answer.
But conventional fluxes, like if you have rational fluxes.
Good, so at phi, the integral of phi of B through a plaquette is P over Q.
It's simpler.
It's still complicated to compute this in terms of P and Q. There's some Diophantine equation you have to solve.
But just conceptually, if you had a constant flux, just to understand, then you can still work in terms of momentum eigenstates. You still have bands.
Good.
Do I understand at least?
So the first question is if you have a magnetic field through a lattice, do you still get a Brillouin zone?
Yes.
And the answer is only if the flux through a lattice plaquette is rational.
That's what you were saying.
So that's the first hard thing you have to do is show that the starting point of having a Brillouin zone is there.
Yeah.
And it is if this flux is rational. And then in that case you can go ahead and compute the Chern numbers
and if it's not rational, then you can't apply the theorem because it will not work. But experimentally, of course, with disorder in addition, things continue to be quantized.
Experimentally, none of this is relevant because the magnetic field you'll need to have some suitable flux through a tiny lattice in a real sample are vast. I mean, the magnetic fields are way too small for this to be of any importance in the actual quantum Hall effects that we're talking about, in gallium arsenide. So I think that this is the reason people just ignored this for 20 years.
Considering that experimentally, so you needed P over Q or whatever for the theorem to apply.
Yeah.
But experimentally, the magnetic field is much smaller.
Orders of magnitude smaller than order 1 through 1.
So then it's not clear if you form. But then if the magnetic field is such a gentle perturbation, can you argue that bands continue to exist?
I think you get so many bands. You get band. If phi is 1 over Q, you get Q bands basically.
So it's very close together, is it?
So I should stress, none of this calculation here is relevant for the sort of things we're talking about in quantum Hall effect. Gallium arsenide, where you see those steps. And it was ignored for 20. Ignored is too strong. Everybody knew about it, but I think it was something of curiosity for 25 years. And it's only recently when it's been realized about topological insulators and you have much more variability in creating these systems. Graphene was discovered by cold atoms, optical lattices. So there's now lots and lots of places where this is interesting and apply it. So I'm really telling you for those reasons, not for the main thrust of these. Any other questions? Do I have to finish at 11:30? Probably it's a good time to finish. Is there a class at 11:30?
I don't.
No, but again, the class will not start.
The schedule has a class. I'm not sure if it's post class. Right?
It's teaching through the break. So
what do people think? Are people exhausted? Because we've made this claim. The next thing is obviously to prove it. And proving it is it's really just algebra. It's taking this and playing around with it until we get that Kubo form.
Related to the Kubo form, right?
Yeah, exactly. What do people think?
Yeah, but the class will start in 2 minutes. Right? I don't think
Okay, so then we
do this. I mean, do it takes time.
Yeah.
Don't. When is the next lecture?
Karthik and Orunapu are in charge of that. So, Orunapu.
The same schedule that is
Wednesday
and Friday.
But what times?
11:30 on Wednesday and 10 on Friday.
11:30.
It was 11:30 Wednesday.
Yeah. You may never go around. You book the room.
No, I have not booked the room. I will do it.
If you change that, just send me an email.
Didn't Rajesh send up to you?
he gets many.